After a quick recap of Unit 3 until Lesson 3.3, let us look into Lesson 3.4, the age of our solar system and all about Sun. The Sun was born 4.6 billion years ago. Many scientists think the Sun and the rest of the solar system formed from a giant rotating cloud of gas and dust known as the solar nebula. As the nebula collapsed because of its gravity, it spun faster and flattened into a disk. Most of the material pulled towards the center to form the Sun. The Sun has enough nuclear fuel to stay much as it is now for another 5 billion years. After that, it will swell to become a red giant. Eventually, it will shed its outer layers and the remaining core will collapse to become a white dwarf. Slowly, this will fade to enter its final phase as a dim, cool, theoretical object, sometimes known as black dwarf. How far is the planet Earth from the Sun? The Sun is at an average distance of about 93 million miles or 150 million kilometers away from the Earth. It is so far away that light from the Sun traveling at a speed of 186 miles per second takes about 8 minutes to reach the Earth. Like all of the other planets in our solar system, Earth does not travel around the Sun in a perfect circle. Instead, it orbits in elliptical shape like a stretched circle. With the Sun just off the center of the orbit, this means that the distance between the Sun and the Earth changes during a year. At its closest, the Sun is 91.4 million miles away from the Earth. At its farthest, the Sun is 94.5 million miles away. The Earth is closest to the Sun during winter in the northern hemisphere. Understanding the life cycle of a star. Stars are formed in clouds of gas and dust known as nebula. Nuclear reactions at the center of the stars provide enough energy to make them shine brightly for many years. The exact lifetime of a star depends very much on its size. Very large, massive stars burn their fuel much faster. The smaller stars and many other last a few 100,000 years. Smaller stars, however, will last for several billion years because they burn their fuel much more slowly. Eventually, however, the hydrogen fuel that powers the nuclear reactions within stars will begin to run out and they will enter the final phases of their lifetime. Over time, they will expand, cool, and change color to become red giants. The path they follow beyond that depends on the mass of the stars. Small stars like the Sun will undergo a relatively peaceful and beautiful death that sees them pass through a planetary nebula phase to become a white dwarf, which eventually cools down over time and stops glowing to become a so called black dwarf. Massive stars on the other hand, will experience a most energetic and violent end, which will see their remains scattered about the cosmos in an enormous explosion called a supernova. Once the dust clears, the only thing remains will be a very dense star known as a neutron star. These can often be rapidly spinning and are known as pulsars. If the star which explodes is especially large, it can even form a black hole. The Sun and its structure. In 1905, Albert Einstein published the famous equation E is equal to mc square, revealing the relationship between mass and energy. This breakthrough allowed scientists to calculate the mass of the Sun and estimate how much longer it will burn as the bright center of our solar system. Interestingly, in that same year, Ernest Rutherford invented radiometric dating. Rutherford's work, including discovering the concept of radioactive half life, paved the way for the radiometric dating of rubidium, allowing us to calculate the age of the Sun. The Sun is 1.4 million kilometers in diameter. The Sun's diameter is 100 times the Earth's diameter. More than a million Earths could fit inside the Sun. The Sun is 300 times more massive than the Earth. The Sun is made up of 2 octillion tons of gas. Inquired what is octillion? 73% of the Sun's mass is hydrogen and another 25% is helium. All the other chemical elements such as carbon, oxygen and nitrogen make up only 2% of the Sun. The sun's layers are different from each other and each plays a part in producing the energy that the sun ultimately emits. We will begin with the core and work out way through the layers. The sun's core is extremely dense and is the source of all of its energy. Inside the core, nuclear energy is being released. In ways we will discuss the sun as a nuclear powerhouse. The core is approximately 20% of the size of the solar interior and is thought to have a temperature of approximately 15 million K, making it the hottest part of the sun. Above the core is a region known as the radiative zone, named for the primary mode of transporting energy across it. This region starts at about 25% of the distance to the solar surface and extends up to about 70% of the way to the surface. The light generated in the core is transported through the radiative zone very slowly. Since the high density of matter in this region means a photon cannot travel too far without encountering a particle, causing it to change direction and lose some energy. The convective zone is the outermost layer of the solar interior. It is a thick layer approximately 200,000 kilometers deep that transports energy from the edge of the radiative zone to the surface through